Hello everybody, welcome to this refrigeration and air conditioning class. Already two classes we have covered. This is the third class. Okay, so in the last two videos we have completed up to which topic? Up to reversed Carnot cycle, right? Reversed Carnot cycle COP derivation. COP derivation. Up to that, we have completed derivation, right? So, what the formula I got? COP equal to T1 divided by T2 minus T1. Okay, I will tell once again, don't worry. But in the last video, in few places, in place of COP, I have written this one, eta. But if I have written eta in the last video, please ignore this eta. Refrigeration efficiency, it will be not expressed in the terms of eta. Rather, it is COP. It will be expressed in the term of COP, coefficient of performance. Reason is there. I will tell later that reason. Right now, only just you understand, you remember. For refrigeration heat pump, this eta symbol, eta term is not suitable. COP is the suitable. COP term is the suitable, right? And one more thing. So in the last video, before this reversed Carnot cycle discussion, I just given the explanation about the Carnot cycle only. Carnot cycle, right? About the Carnot cycle, I explained first in the last video. Then I came to the reversed Carnot cycles with the PV and all PV and the TS diagrams. Okay, TS diagram, PV diagrams. Okay, several properties. Okay, T1, P1, S1, S2, like this we have discussed. So what is I think in this Carnot cycle explanations, while I was doing the explanations, I have done small mistake in the PV diagrams. Okay, let me once again I will do. Please ignore that part where I have done. While I drawn this diagram, PV diagram actually. This is 1, this is 2, and this point is 3, and this point is 4. This 1 to 2, the naming here, the process name I have given, I think it is given wrong. It is called isentropic. It is called isentropic expansion process. Then 2 to 3 is called isothermal compression process. And this 3 to 4 is called again isentropic compression process. And the last one, 4-1 is called isothermal expansion process. This is the correct order of the name of the processes, right? In the last video, I think I have done exchange in between. This is compression, expansion, compression. I have exchange among these four processes. Okay, so this is the last class rectifications. I have just shown you what mistake I have done in the Carnot cycle PV diagrams, right? Only the name I have given, I think it is wrong, right? So then I discussed about the reversed Carnot cycle. Also PV diagram, TS diagram I have done, COP also derived. Sir, here what are the in the reversed Carnot cycle? Okay, Carnot cycle. What are the four processes we have used? First one is what? First one is isentropic reversed Carnot cycle, not Carnot cycle, right? Reversed Carnot cycle, isentropic compression, right? Isentropic compressions. Next, isothermal. Okay, isothermal expansion. Next, isentropic expansion, right? And last one is isothermal compressions, right? So these four processes, 1, 2, 3, 4 processes, we have used in which cycle? We have used in reversed Carnot cycle, right? Reversed Carnot cycle. PV diagram also there, TS diagram also there in the last video you observed, right? So in that, what we got actually COP, what calculation we have done? So COP calculation, right? And observe COP calculated in the last video. Okay. So what the COP value I got, sir? COP equal to T1 divided by T2 minus T1. What is this T1? T1 is, okay, lower temperature. So many names. Freezer temperatures. We can say cooler temperatures. We can say inside temperature, or we can say evaporator temperature. Okay, why? Because this much name I'm telling, because in the problem, okay, in the numericals, it may be mentioned in the problem any name, then you need to remember that it is the inside of the temperature or evaporator temperature, or it is also lower temperature, minimum temperature it is, okay, minimum temperature. And what is this T2? T2 is called higher temperature, or it is called condenser condenser temperature, or it is called, what is that? It is called outside temperature, outside temperature. This much names are there: evaporator temperature, sorry, condenser temperature, outside temperatures, or it is called high temperatures. Sir, in the reversed Carnot cycle, I have discussed that four process. First process is what? Compression, isentropic compressions. So let me draw the schematic diagram here, so that it will be uh, more clarity for you. It will bring more clarity. So this is the compressor, right? Next, here crackers sound guys coming. Okay, no. These are called condenser. This is called condenser. Okay, condenser linings, and this is called this one is called expansion device, right? Expansion device may be a turbine, may be a cylinder piston arrangement, anything. This is called evaporator. Next, pipeline connection is there from here to here, and here to here, here to here, and here to here, right? So in the last class we have discussed, but schematic diagram I have not done. That's why. So this is the compressor. This is called compressor. This is condenser, and this is expansion, and this one is evaporator. Main parts, right? Main parts of the refrigeration system. Here 1 point, suppose 2 point, 3 point, and 4 point. But but one point, the working fluid enter. These are the pipeline actually. Okay, these are the pipelines, here to here to here to, all are pipelines. So the pipelines, several parts of the refrigeration system. I mean, compressor to condenser, condenser to evaporator, sorry, condenser to expansion, expansion to evaporator, pipelines. Inside this pipeline, air is flowing. Air is the refrigerant. Air is the refrigerant. So one point it is entering, 2 point it is exit. So at 2 point, air is entering to the condenser, and at 3 point it is exit. At 3 point, it entered to the expansion cylinder, expansion device, and it exit from the 4 point, and 4 point it is entered to the evaporator, and 1 point it is exit, again 1 point it is entered into the compressor. So like this cyclically it will be happen. That's why it is called cycle. Okay, so in this compressor, which processes out of 4 processes, which processes are happening in this compressor? Remember, in this compressor, isentropic compression process. Okay, in the compression process. Okay, in the condenser, which process? In the condenser, isothermal expansion process. In the expansion device, isentropic 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 expansion process. Okay, expansion process. And last one is in the evaporator, which process is executing or happening here? Isothermal, which one? Isothermal compression process. Right? These are the several processes executing or performing here in these 4 devices. Okay, compressor, condenser, evaporator, and let me give you some few clarity on this. What is this isothermal? What happened? And what is this isentropic compression expansions? Okay, let me give you some explanation on that also. Observe. Very interesting that is also. One minute. Just save. To save. Control N. Enter. Okay. Observe. Sir, let me tell you about isentropic process versus isothermal. What happened in this part? Isothermal actually. Isothermal process. Okay. What is this isentropic process? Isentropic is also called as reversible adiabatic process. And this isothermal is also called as constant temperature process. Okay. Sir, what is the meaning of this reversible adiabatic? What happened in adiabatic process? In adiabatic process means no heat interaction. Okay. 1 minute. Okay. No heat interaction between system and surrounding. Okay, no heat interaction, then it is called adiabatic process. And what is my reversible adiabatic? Suppose one is a state and two is a state, another state. Okay, so one is the state, two is the another state. Then state in the terms of thermodynamic state, one is a thermodynamic state, two is the thermodynamic state, and 1 to 2 it is connected by path. This is called path. Okay, if a process 1 to 2, it is a process right now. 1 to 2 is the process. If it is go in this forward direction from thermodynamic state 1 to thermodynamic state 2, and again if it reverse in this direction from thermodynamic state 2 to thermodynamic state 1, then it is called reversible. Okay, reversible. Okay, going from 1 to 2 and coming from 2 to 1, nothing but reversible. Suppose what is irreversible? Sir, going from 1 to 2, 1 to 2, but coming from 2 to 1 dash is called irreversible. Okay, it is called 2 to 1 dash. Going from 1 to 2 and coming from 2 to 1 dash is called irreversible process. So but here reversible adiabatic, that means 1 to 2 it will go and come back in the same path 2 to 1, and during that movement no heat transfer. Okay, no heat transfer. Are you thinking this? Okay, 1 to 2, 1 to 2 process, you have to move, you have to execute, and during that executions no heat transfer. Practically this kind of process is not exist. Okay, not exist. Practically it is not exist. Okay, but by assuming something, by assuming some cases or some parameters, we can make it available. Reversible adiabatic process, we can make it available, but practically it is impossible, it is not available. But by assuming something, okay, by assuming something, we can make it available, right? What is that assumption means? What is that assumption means? Reversible adiabatic, right? Adiabatic means what? No heat transfer. Heat transfer will be zero here. Q equal to 0 here, right? But practically never q be equal to 0 during a process, right? Observe, definitely heat transfer must be there. So practically it is not possible, but by assuming some cases, we can make it reversible. What is that assumption, sir? Observe, suppose this is a point A and this is a point B. Here is a body is there. General example I am getting. General example. So you are being told here, you have to move this object from A point to B point, but this object should not be shaked. I mean, should not be vibrate. Without vibrations, okay, without vibrations, observe, without vibrations, you need to move this object from A point to B point like this. A point to B point, you need to move this object, right? Sir, but without vibrations, vibrations should not be there, body should not be shaked. Then is it possible practical? No, it is never possible, right? Because earth movement is there. Na? Okay, vibration always will be get vibration. Definitely very less amount even also will get the vibration. Without vibration, it is not possible. But now if I'll assume here, suppose the observer here, he is the referee, suppose. He is the referee, he is going to judge. He is going to judge you whether you have done the task properly or not, right? That means without vibration or shaking, this object you are able to move from this place A place to B place or not, is the referee is going to check here. Then I know, you know, without vibration it is not possible at all. Without vibration the object cannot be moved from here to here, right? Okay, 1 minute. The object cannot move from here to here like this. Vibration must be there definitely, because some external forces will be affect on that, so that vibration must be there. But what I will do here, observe, when this particular referee, for even 1 second also, he will be in absent mind, then immediately what I will do, immediately I will move to here to here. That means that movement is not in the knowledge of this referee. Suppose he for 1 second he is disturbing, he is looked to any other place. For 1 second, I observed carefully. He is looked. During that 1 second, I moved this body from A point to B point. Now I will tell after a moment, okay sir, I moved without checking. How it is possible? How it is possible, sir? Because very fast I moved this object here to here, very fast, so that within 1 second from A point to B point it is reached, right? Suppose in place of very fast, I will move it slowly, 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 slowly. Is it possible that the body will be not vibrate and that situation will be not observed by the referee? It is not possible. While you will move it the body very slowly, 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 definitely after 1 second the referee maybe look at you, look at the body. Hey, body is vibrating here, body is vibrating here. But instead of moving it is very slowly, within that 1 second of time I moved very fastly, very fastly. That means unknown of that referee. Then what I can claim, sir, body movement here done, but no vibration happened, no vibration happened. That means from this example, what is the conclusion? Conclusion is very simple here. This reversible adiabatic process, what I told, heat transfer not be possible. But what I will do, if I'll move that, if I'll move that process from 1 to 2 very fast, very fast, then I can claim, the process moved to 1 to 2, okay, without heat transfer, without heat transfer. But practically, if it is passed very slowly from 1 to 2, okay, very slowly, then anybody, the referee can easily know, okay, heat transfer is happening here. But suddenly he is unknown, he is looking any other wares, and during the time you movement the process 1 to 2 very fast, then he cannot able to know, oh, nothing will be happen, oh, heat transfer, nothing, heat transfer not happened here, just like this body movement, right? So the conclusion is here very simple, is what? Reversible adiabatic process. Okay, reversible adiabatic process is what? This process should be very fast, should be infinitesimal fast. We cannot imagine infinitesimal fast process. Then only we can assume that. I told an assumption. What assumption we are doing here? Assumption is what? If the process become very, very, very fast, then reversible adiabatic process is possible, otherwise not possible, right? So remember one important point: reversible adiabatic process should be a very fast process, right? So that means no effect changes will be visible to the referee, visible to the users, visible to the people, right? So it should be very fast. In the other hand, if I talk about this isothermal process, observe, isothermal process, it's just opposite to the reversible adiabatic process. How it is? Observe, I will tell that one also. One. Control N. U. Now, what conclusion I got? Now, reversible adiabatic process should be very fast process, very fast process, right? Similarly, what about this isothermal process? I will tell isothermal process. Observe, sir, isothermal. Suppose this is one body, this is one body. Isothermal means what? Temperature constant, temperature always constant. And suppose this is another body, this is another body, right? This is another body. Now what I will do here, if I will slide this body, okay, if I will slide this body on this first body, second body, like this, if I will slide this body, what will happen? Heat generated or not? If I will slide this body on this body, suppose this is, okay, I will give the name also. This is suppose body B, this is body B, and this is body A. What I will do, suppose I will slide this body here like this I will slide, like this I will slide on the body A. If my speed is very fast, if my speed is very fast like this, then immediately heat will be generated, okay, and temperature will be changes between the contact surface. Between the contact surface, temperature will be changes. But isothermal process, the temperature should not be changed. Then how here also what I will do, instead of moving this body very fast, I will move this body very slowly like this, very slowly, like this, very slowly. Infinitesimal slow movement I will do here. Then what will be happen? Between the contact surface, there may not be any heat will be generated and temperature will be not change here. But whereas if it is very fast, immediately it will be generated, temperature will be changed. Whereas it will be very less, very low speed, a very low speed, then what will be happen? Heat will be not generated and temperature will be not changed. Then only I can say the process is isothermal process. Okay, process is isothermal process. And what is the conclusion here? For isothermal process, for isothermal process, okay, for isothermal process, the the process should be moved, the process should be move, okay, very slow, very slow. Okay, adiabatic is very fast, isothermal is very slow. To maintain the temperature constant, I need to move that process, or the process should be moved from one point to another point very slowly, very slowly. And here, in case of adiabatic process, uh, to experience no heat transfer between system and surrounding, then I need to move the process from 1 to 2 very fast, very fast. It is fast process and it is slow process. This is the two important point you need to remember. Okay, why it should be very fast, why it should be very slow, through example I explained here, right? One minute, right? So in the reversed Carnot cycle, the four processes are reversed Carnot cycle. The four processes are, this is the TS diagram. I will draw TS diagram. TS diagram. Okay, this is the four processes diagram actually. 1 to 2, 2 to 3, 3 to 4, 4 to 1. This is called isentropic process or reversible adiabatic. Isentropic. This one and this one. Isentropic or reversible adiabatic. And this one is called isothermal. Observe carefully what is the problem here. And this is also called isothermal. Isothermal. How the cycle is moving? 1 to 2, 1 minute. Isothermal. We change the color. How the process is moving? The process is moving 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Again 1 to 2, 2 to 3, 3 to 4, 4 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 1. Like this, the process is executed, cycle is completed. If you observe carefully the total cycle, observe, this is the isentropic I told, which is very fast process, and isothermal, which should be very slow process. Again this side for 3 to 4 isentropic, again it is very fast process, and again isothermal, it is very slow process. Okay, slow process. If I'll see the cycle, one process is very fast, suddenly another process is very slow, suddenly another process is very fast, again slow. This kind of concept practically not possible. Very slow, very fast, fast, very fast, then very slow, very fast, very slow, very fast, very slow. This kind of process, this kind of cycle, it should not exist, not exist, not exist. If it is practically exist, then what will be happen? Problem will be happen, accident will be happen. Suppose bike you are riding, right? You are riding the bike here. You are riding the bike here. Okay. You are riding bike here. Very fast, suddenly very slow. Again very fast, suddenly very. The people are doing, the young generation are doing likely only. But what happened? It will affect the bike performance, right? After a few days, the bike is going to be damaged, or maybe accident may happen or not. So this kind of things practical is not possible. One fast process followed by slow process. One again fast process followed by slow process, practically not possible here. So this is the biggest limitations of the Carnot cycle, reversed Carnot cycle. Okay, this is one more the biggest limitations. Sir, what is the limitation of the Carnot cycle? Why practical it is not used? Because it consisting of such processes. Okay, such processes that nature is what, very fast and very slow, and they are followed to each others, so it is practically not possible. So this is the limitations, right? Second limitation is what here? Second limitation, observe second limitations. So here this person 4 to 1 isothermal process, and 3 to 2 to 3 also isothermal process. Here is the second limitation. What is that? See, 2 to 3, no temperature changes. No temperature is constant. Here also 4 to 1, no temperature changes, temperature equal to constant. But heat transfer happening or not? Yes. Heat transfer, this is heat transfer Q1 and this is heat transfer Q2. Okay, heat transfer Q1 and heat transfer Q2. In the first class, I have told one diagram. So, latent heat and sensible heat, right? In latent heat, what happens? Heat transfer will be there, but temperature will be not change. But sensible heat transfer will be there, but temperature will be increase or decrease. Temperature will be change. But latent heat, what? Temperature will be latent will be there. Heat transfer will be in latent heat. Heat transfer will be there, but temperature remaining constant. Okay. But here, and one more thing, in latent heat, what happening in latent heat? In the previous example, what I told about the latent heat, until the all solid ice converted to liquid ice. This is latent heat portions, and again all liquid converted to vapor. Okay, this is the portion of the latent heat. Observe, temperature constant, heat is continuously supplying. What result happening here? Temperature constant, but what one result is happening? What? Phase change. Solid to liquid, liquid to vapor. Solid to liquid, liquid to vapor. Phase change is happening. So during that latent heat period, temperature remaining constant, but phase change is happening, right? But here in the reversed Carnot cycle, what is the working fluid? You know, working fluid is air. Working fluid is air. So while air should be passed 1 to 2, 2 to 3, 3 to 4, 4 to 1, air should be changed its phase between 2 to 3 and 4 to 1. But sorry. Okay, air should be changed its phase between 2 to 3 and 4 to 1. But practically air does not change its phase. Does not change its phase. Right? Air never changes its phase. Throughout the cycle, air stay in gaseous phase. 1 to 2 process, 2 to 3 process, 3 to 4 process, 4 to 1 process. In every process, the air is going to be stay in gaseous stage only. But here 4 to 1, latent heat concept is there or not? Temperature constant. 2 to 3, temperature constant. Latent heat concept is there. Then if latent heat concept is there definitely phase change should be happen. Then only the latent heat concept will be satisfied. But here temperature constant, but air does not changing its phase. That means it is practically impossible. The total cycle is practically impossible here, right? So two limitations I told. What is the first one? First one is one process is fast, another process is slow. First slow, that is not possible. Second is what? So in the reversed Carnot cycle, in the two portions, right? I will tell one second. Observe. In the two portions, what are the portions? Here one portions. This is the TS diagram. Okay. So 1, 2, 3, 4. This is compression, isentropic. This is isothermal. This is temperature constant or not? T2 equal to T3. And this is T1 equal to T4. So temperature constant. That means here heat transfer happening. Here heat is rejecting and heat is extracting here and heat is rejecting here. Q2, heat rejection. This is rejection and this is extraction from inside of the refrigerator. So heat transfer is happening. Temperature is constant. Okay. Heat transfer is happening. Temperature is constant. That concept is nothing but latent heat. But in latent heat, what happened? Definitely phase change must be there. Phase change. Okay. Okay. Now phase change. Either solid to liquid or liquid to solid or liquid to vapor or vapor. But here, what is the working fluid? Air is the working fluid. Throughout the cycle, air is moving. Air is moving. So air does not change its phase. Okay, air is always in gaseous phase only. It never solid. It never going to be liquid. It never going to be okay. Convert one form to another phase, one phase to another phase. So since this cycle, reversed Carnot cycle is what practically it is not possible. These are the limitations here. So what is the advantages here? Advantages is what? Advantages is what? This is a role model. First advantage is what? This is a role model. Role model. Okay. Role model of okay all refrigeration cycles. All refrigeration cycle. This is the role model. This is the base cycle. The idea to develop the refrigeration cycle or to improve the coefficient of performance of the refrigeration cycle, that is comes from this reversed Carnot cycle. Okay, that is comes from this reversed Carnot cycle. That's why it is called the role model or base cycles. So what is the next advantages? Next advantages of this reversed Carnot cycle is what? Uh, the formula for this COP equal to T1 by T2 minus T1, right? T1 minus T1 divided by T2 minus T1. By changing this T1 T2 by adjusting this T1 T2, I can get about maximum to maximum COP max. Okay, 100% efficiency I can get if I'll slightly adjust this T1 value or T2 value. Okay, by adjusting this T1 value and T2 value, I can get 100% performance here, 100% performance here. But 100% performance or 100% efficiency, no machine is going to give. No machine. But by theoretically, if I'll change this T1 T2 value, suppose T1 is 5, T2 is 8 minus 5. If I'll vary this 2 3 value, I can get what 100%. Result is what 100% performance. But no machine practically is not ready to give, not giving actually 100%. So this is what are advantages. Okay, this is called advantages. First advantage is what? This is the base cycle. Base cycle or role model for other refrigeration cycle. Okay, role model. I'm not writing properly, but what I'm telling, you just observe carefully. You can make it note also. What sentence I'm telling, that is important. Writing is not important here, right? So whenever it is required, I will write properly. Then what is the next advantages, sir? By changing this T1 and T2 value, we can get 100% performance for that machine, but practically 100% performance no machines. These are the advantages. Demerits what? Demerits what? one process is fast, another process is slow. So fast slow concept is not a practical. Fast, slow, then fast, then slow. It is not practically possible. Okay, so limitations. Second limitation is what? So latent heat concept is the second limitations. Okay, temperature during the 4 to 1 process and 2 to 3 process, temperature is constant, but heat transfer is happening. Okay, so heat transfer is happening, but temperature constant. That concept is called latent heat. In latent heat, phase change definitely has to be done, but here air does not change its phase. That's why this is the limitation. Air does not change its phase here, right? Does not change its phase. This is the limitations here. Okay, so one more important thing I will tell you here, then I will conclude. Observe. Sir, what expression I got? COP equal to T1 divided by T2 minus T1. See, suppose in this expression, suppose T1 value is suppose 4. Okay, 4. And T2 value is suppose 20. This is T1 value. And T2 value is suppose 20. Then what is the COP, sir? COP become 4 by, okay, T2 value you take, instead of 20, you take T2 value, suppose 6. Okay, 4 and 6. Okay, so T1 value is 4, T2 value is 6, and T1 value is 4. What is the answer, sir? What is the answer here? 4 by 2. What is the answer? 2 I am getting. COP value is 2. Now, in place of T1 4, T2 is fixed. Suppose T2 is fixed to 6. It will not change. Suppose, assume. Now T1 I am changing 4 to 5. Okay, 4 to 5. Then what will be happen, sir? Observe. COP value is 5, T1 value is 5. T2 value not change 6 minus 5. What is the answer? 5 by 1. See, COP increase or not? Here in the previous case, COP was a 2. In the latest case, COP become 5. That means COP increases or not? Yes, COP is increases. In the same way, suppose in the T1 value, in place of T1 value 4 or 5, I will take 3. Then observe COP become 3 divided by 6 minus 3. So 3 by 3. What is the answer? 1 or not? Then COP decreases. Na? Sir, what conclusion we can draw from this explanation? Sir, COP value, okay, observe. COP value increases, okay, increases if T1 value increases. And COP value decreases if T1 value decreases or not. Okay, T2 is fixed. Just I gave several situations here. Okay, by varying the T1 value 4, 5, and 3, I got COP in different. What conclusion? COP will be increases if T1 increases. COP decreases if T1 decreases. Right? So this is the conclusion I got here. Okay, observe here. Sir, this is the refrigerator. This is the refrigerator inside. This is compressor, and this is condenser. This is expansion cylinder. Okay, like this cycle is there. This is the inside of the refrigerator. My refrigerator here. Okay, here the refrigerator. And here evaporator means this is the lower temperature T1. Here the air is flowing at temperature T1. And here air is rejecting to the outside heat, temperature is T2. Right? This is T1 and this is T2. And here I have put some items, substance I have put here. Food items, cold drinks, everything I have put here. Observe what conclusion I got just now. Sir, if T1 will be increased, then COP will be increased. Okay, T1 will be increased, suppose COP will be increased. Suppose right now T1 is 4 degree. Now I increase to 5 degree. Now I increase to 6 degree. Now I increase to 7 degree. So slowly, if I increase the T1 value, what will be happen? COP value will also increase or not? It will be increased, it will be increased. Now, in place of 7, it become 10 degree. Again, COP will be increased. Oh, very nice, sir. I can get more COP. 12 degree, 18 degree, 20 degree. I will increase like this the temperature. But suddenly, suppose this inside temperature is how much? Inside temperature is suppose 15 degree. Inside temperature is 15 degree or 10 degree, any temperature you take inside of the refrigerator temperature. Sir, up to 14 degree it was okay. Okay, up to 14 degree. T1 temperature is 14 and inside temperature is 15. T1 temperature is 14, inside temperature is 15. Then heat transfer can be easily happen or not from inside to air. But once it is become 15, okay, this temperature same, then heat transfer cannot possible. Cannot possible. Heat transfer is not possible. Now suppose I am increasing 15 to 16 because more COP I want. So if I'll increase the T1, I'll get COP just from the expression I came to know that expression derivations. So I instead of 15, I kept it to 16. Then what will happen? This temperature is T1 temperature is more and inside temperature become less. So instead of heat extraction here, heat will be what will happen? Heat will be flow in the reverse direction to the refrigerator. Right? Very important point. Observe. Sir, observe. Sir, what you told? If T1 increase, COP increase. Then suppose inside temperature of the refrigerator is a 15 degree. Okay. And this air temperature, refrigerant temperature is suppose 4 degree. So, okay. So just I came to know, sir, this T1 value I will increase. Then COP of the machine will be improved. So I increase to 5, sir, no problem. Because here 15, here 5. So 15 to 5 heat transfer easily happen. Then the heat will be carried by the compressor and rejected. Right? Then 6, okay, no problem. 7, okay, no problem. 12, okay, no problem. 14, okay, no problem. But when this T1 value become 15, okay, and inside temperature also 15, then temperature balance, then no heat transfer will be happen. Now T1 will become 16. T1 will become 16. Then what will happen? Instead of a heat transfer from inside to outside, what will happen? Heat transfer will be done from outside to inside. Outside to inside in the sense from inside to the refrigerant, heat transfer will be start from refrigerant to inside. But refrigerant we are using to take the heat. But in this case, refrigerant will be give the heat to the inside. So instead of cooling, heating will be happen. And what is the conclusion, sir? Sir, you told T1 value I will increase, COP I will increase. Then remember, up to what range the T1 value should be increased? Up to what range? I should not increase this T1 value. Okay, I should not increase this. I should not increase this T1 value. Okay, T1 value beyond what? Beyond inside temperature of the refrigerator. Inside temperature of refrigerator. Okay, if you'll exceed the inside temperature of the refrigerator, then heat transfer instead of inside to refrigerant, okay, it will flow in the reverse direction, refrigerant to inside. Okay, so this is the temperature limitations for T1. Temperature limitations for T1. Right? Temperature limitation for T1. Same way for temperature limitation for T2 is there. Observe, I will tell that one also. Sir, expression is what? COP equal to T1 divided by T2 minus T1. Right? Sir, T1 suppose 4. T2 suppose right now 6. Or suppose 8. Suppose you take 8. Then what is the COP, sir? 4 by 8 minus 4. COP is 1. Now what I will do, I will change the T2 value. T1 is fixed, I will change the T2 value. So suppose 8, I will increase to 10. Then what is the COP, sir? 4 divided by 10 minus 1. Yes, sorry, 10 minus 4. Then it become 4 by 6 or not? Sir, if it is 4 by 6, then definitely the value will become 0 point something. Okay, 0 point, suppose it will come 0 point 14 6 6 0.66 around the value will come. Okay, now suppose instead of 10 I will take the T2 value 6. Then what will happen to COP? T1 value will not change. 4 1 by 6 minus 4. Observe, 4 by 2. What is the answer I am getting, sir? 2 or not? Sir, what is the conclusion here? Sir, COP will be improved if T2 decreases. Okay, so I decrease from 8 to 6. I got COP 2. I increase 8 to 10, but I got COP how much? 0.66. That means COP of my machine can be improved by decreasing the T2. But in the previous case, with T1, COP increases, with T1 increases. And right now, COP increases with T2 decreases, right? Okay, two concept, very, very important. T2 concept, right now. So observe, I will show the in diagram also what conclusion we draw here and what is the temperature limitations there. I will show you. Observe, so this is my condenser and this is expansion cylinder, this is evaporator, and this one is my compressor. Okay, so this is inside, right? This is inside, and temperature is here, air is flowing, refrigerant is flowing, temperature is T1. Here also refrigerant is flowing, temperature is T2. Okay, T2. Sir, what you told just, sir, if T2 decrease, then COP will be increase. Right? COP will increase. Suppose you assume this T2 value is what? T2 value is suppose, because this is high temperature, na compressor. From compressor it is coming, pressure is more, temperature is more. Suppose the temperature is 35 degree. T2 temperature is 35 degree. And during that time, the surrounding temperature, atmospheric temperature is suppose 30 degree. So 35, okay, 35 and 30, 35 and 30. So which one is the more? 35, na? Then easily heat can be transferred from system to outside or not? Yes, from system to outside, and that is the expectation, that is the required actually. Heat should be rejected to outside. So when it is possible, when T2 value is more and surrounding temperature is less. T2 value is 35, surrounding temperature is 30. But sir, what you told right now, if T2 value decreases, COP increases, then what I will do in place of 35, I will make it 34. Okay, T2 value 34. Surrounding temperature is what? 30, na? Sir, 34, 30. Heat transfer can be done. Okay, no problem. Sir, now this time 33. Okay, sir, no problem. Heat transfer can be done. Now, sir, 32. Decrease, na? If I decrease, COP increase. Okay. Okay. See, if T2 decrease, COP increase. That's why I'm decreasing the T2 here. 33. Okay, no problem. Right now, 32. Okay, sir, no problem. Heat transfer also 32 to 30 can be easily done. Now 31. Okay, 31. Okay, sir, 31 also happy. Now 30. So now T2 value 30. Surrounding 30, no heat transfer. Now, sir, COP now increase na, sir, 29 or 28. What will be happen? Instead of heat move in this direction, now this temperature become 29, whereas outside temperature is 30. Instead of heat transfer in this direction, heat transfer will be done in this direction, right? In these directions, then what will be happen? It cannot be rejected. My system is going to be fail. Total my machine is going to be failure. Then, sir, what conclusion you told? If T2 decrease, COP decrease. Sir, I am decreasing the T2, but after some times it is not happening properly, not giving the proper result. Why? Because condition, limitations. Okay, conditions. No doubt T2 decrease, COP increase, but up to what range I need to decrease the T2? The T2 should not decrease below atmospheric temperature, ATM temperature. Okay, if it is 30, right, if it is atmospheric temperature is 30, then this T2 value should be greater than 30. It may be 31. Okay, it may be 32, right? So don't keep more difference. Suppose you are keeping 40 to 30, COP automatically less. Suppose 30 to 30, less difference, so COP automatically improve. But you should not make, okay, if T2 decrease, COP increase, you told you should not make 20 degrees, then it will be transfer in reverse direction, right? So this is the called temperature limitation. Okay, temperature limitations. Temperature limitation, this concept is called, right? So COP equal to T1 by T2 minus T1. What is the temperature limitations? So T1 will increases, COP increases, but T1 value, T1 should not more than inside temperature of refrigerator. Okay, and T2 decreases, COP increases, but T2 should not less than, okay, less than ATM temperature, atmospheric temperature. This is the conclusion. What is the topic, sir? Temperature limitation, right? Very important, temperature limitations, right? So this is the topic. Today I discussed about the Carnot cycle, reversed Carnot cycle. This reversed Carnot cycle is over. Next, I will discuss Bell-Coleman cycle. Bell-Coleman cycle I will discuss in the next video. So please take care. I am concluding here.